Hi everyone, again welcome to this lecture. Today we will be continuing the Linux networking lecture. Before we begin, actually let me recap what we did in the last lecture. We actually started talking about the networking and we defined what the network is. Essentially the networking is how multiple computer or components they communicate with each other. We started actually we then also corrected our terminology. These computer components, they are all called nodes, and we will be talking about nodes. And then we also talked about the four main characteristics of the network, which is the size, which we measure as WAN, LAN, etc. Topology, like various types of topology, various types of configuration, how they are all connected physically. And then there's a physical characteristic also, which is what kind of wiring is used, whether it is fiber channel, whether it is copper. We do it in terms of 10 base T or 100 base T kind of measurements. And then finally the protocol, essentially how they talk to each other, which is TCP is one of them, UDP is the other one. So we talked about this, and then one of the concepts that we introduced during this lecture was this open systems interconnection model, or OSI, which divides the whole networking into the 7 layers with varying degrees of complexity. The application layer, where you have the complete visibility of the application, where you are launching the program, you are sending the program to a particular network, and then once that program is once you decide to send and to hit the send button, how it is then transmitted. That's what the OSI deals with. Like the various layers are the presentation layer, then it goes to the session layer, and then it is the transport network, data link, and then the physical. Physical is where the actual communication happens through the wires, and basically the bits are transmitted, and we don't even call it bits. It's basically just the voltages. In fact, way of looking at OSI is from the bottom to the top, which is the normal way that people always try to teach, because it's easier to understand that way. So you talk about like how the bits are transmitted, like with voltages. Then the data link layer, which essentially forms the framing of the data. Then it goes into the network layer, where it's basically it has the IP forwarding also built in, and then it goes into the transport layer, which is which offers the end-to-end reliability of the system. And then the upper layers are the session layers and presentation and application, where the data is aggregated even more, and then when it reaches the application, the computer actually sees the complete picture or the full data set. All the headings, everything, it's eliminated, and then now you get the pure data. So example, we also talked about how the OSI model differs from TCP/IP. The TCP/IP, the top 3 layers are combined into one, and then essentially all the upper level applications like mail, web, etc. they reside in the application layer, and then progressively, you add more bits. Basically, you break up the data, and then you put how you broke up those kind of roadmaps into those broken up pieces, and then send as piecemeal into the various layers below, and then the layers below, then they can communicate. We also saw like there was 16 or essentially like 5 words, sorry, 6 32-bit words, which constitutes the IP header, which is used by the IP layers, essentially, like there is this network layer to forward the messages. And then we also saw how the various points differ essentially, like how a host is different from a router and how far higher the chain that the message has to travel before it is distinguished and then it is routed to the appropriate destination. So we saw some of those examples. I also wanted to put this picture here, which kind of summarizes all our discussions so far. As you know, like I mean, the Ethernet layers are the lowermost layers, which then this is the link layers essentially, which goes into the network layer, which is the IP layer, and then you have the transport layer, which is the TCP layer. So these are all buried under the bottom of the chain, whereas the kernel actually like has all these things basically. So all these correspond to the kernel side, and then the user just sees the top level. And we also saw an example of a client server architecture where the client opens up some communication channel. It actually opens up something called a socket. So essentially, like the server creates a socket, it binds an address to the socket, and then it basically waits at that point. Whenever the client wants to communicate, client also creates a socket, and these sockets are matching, so basically you can connect. And once it sends that message to that appropriate socket, and the server has the socket, it sends back another message to accept that socket. At that point, the connection is made, and then the packets are sent one by one into the server, and then server services, and then it sends back those packets as well. So the send and receive goes hand in hand. This simple client server model is used in many applications. One of the key things that we learned was also the HTTP, how we open up a website, or essentially like when we make a server service request, how that gets into the server, and then how server services that request. So in the data centers, you will find this used a lot. In fact, one of the structures of a data center is that basically they also divide into layers where there is a specific HTTP service layer, and then followed by an application layer, and then followed by a database layer, which all of them work hand in hand to provide the best service possible for the user. So that's the big introduction. Today I'm not going to ask you to do any exercises or activities. We will combine a lot of these activities into one big lab for this session. Today the main topic is going to be the IP addressing. This is one of the topics I think is important from a general understanding perspective, mainly because as VLSI designers, you will be in situations where you have to make sure that how to debug a network, and probably you may have to also correct some of the issues that are in the network, and all of them like by remotely logging in, and then you may also even do some little bit of system administration. Again, as I mentioned earlier, this entire course is not to make you a system administrator. This still focuses on the usage of the systems. So we will only be doing that, but I still wanted to give you like a little bit of basics on the IP addressing, so that you are well prepared. Like I mean, if somebody says that, hey, this is your network address, or this network is not working, or the subnet is not working, or something like that, then you know what they mean and how you can give them that information. So with that introduction, let's go into the IP addressing. So the first question that we ask is, what is the purpose of IP address? Why do we need the IP address? So IP address is unique identification of the source. So sometimes like you can use it for security and policy based filtering of data. What this means is you can avoid certain or you can bounce back certain sources of from where the service request is originating. The other one is when it originates from a low level server or a high level server. Based on that, you can set priority and you can set which data needs to be taken in and which data needs to be rejected. And then the IP address also provides a way to uniquely identify a destination so that the networks know where to send the data to. So you need to have an IP address to receive the data, while as a receiver of data you will be checking the IP address of whichever the message that is coming in. So in fact the network administrators use the IP address in a very effective way this way. They try to block certain network. They identify the networks based on their IP address so that they can put it in the block table so that even if you try to go there, they can block it. Typical example, as you know, like pawn sites and things like that, basically where you cannot get into like from a public computer or a university computer or even like a work computer. The reason is the IT department knows the IP addresses of those systems and then effectively block from any messages going to those IP addresses. Usually this is an network independent format. That's what you need so that it is not tied to a given network. And one of the reasons why internet became popular is also because of this feature where it is not tied to any network, any particular type of network. So it is basically IP can be over anything. So this is another key thing to remember. So what does it do actually? So let's look at that. So the IP address identifies a machine's connection to a network. So whenever a network receives a message, it knows essentially like which machine actually originated the request. There are no like spurious requests coming into the network which can destabilize that network. When you move from machine to machine, even like physically moving a particular machine from one network to another network, it requires a change of the IP addresses. So in fact this has become an issue because say like you actually change providers of internet service and then suddenly new provider comes in and then you have to now your IP address is all different and everything else is different. That is okay, but when you buy a new computer or when you change a router in your home system, you don't want everything to be different. So there are ways to actually also control this one. There is like dynamic IP allocation. That's what most of the internet companies do because they know that the service is to just one node, but inside that node, if you change anything, they don't really want to know because as long as they can uniquely identify that it is you who is originating all the messages, they are okay with it. So this dynamic IP addressing actually has become pretty popular. So up to your point, it may be a static one, but then inside that you can make it into dynamic. And then TCP/IP uses a unique 32-bit address, and let's look at how they use this 32-bit address in the next slide. Um, so it is a 32-bit number divided as 4 octet number, so it's 8 bits. So the representation will be like, you can say 133.27.162.125. That's one IP address. So that's the decimal representation. In binary, you can also like represent this into the following. Here you can say basically that it's 1000 0101. So that represents this 133. It's a single number, and then 27 is represented as the 11011, and then 162 is again 101000010, and then same for 125, which is 01111101. Sometimes this is also represented in hexadecimal. For example, the same number can be like 85 1B A2 7D. In Linux systems, typically, like people represent their IP addresses in the, or they call out the IP addresses in the hexadecimal. In fact, there are some commands which we will talk about in the later part of the this lecture. The commands to get data from your machines and see like how they are represented. So we'll talk about that later. So now let's look at how these IP addresses are allocated. As I already mentioned, there is a static IP address, which is what was very prevalent until they ran out of the address space, and then they started doing this dynamic. And then dynamic also used to solve certain issues where the providers don't want to know like how many computers are connected to the network. They want to know like in terms of the number, but they don't really care which ones are connected. Today in a typical home you can find up to like maybe 10 devices connecting into the internet in various forms. Sometimes they're all like connected together very easily. Like you can count your TVs, where the TVs are connected, all your mobile phones are connected, the computers are connected, printers are connected. I don't know, maybe even like your alarm clock, whichever one you can think of, they can easily be connected to the network. Oh yeah, network storage is another big thing right now. So that's another attached storage. So now if you add up all these things, 10, 15, easily it will cause that number. And so the key question is, how do you provide unique addresses to all of them? So let's look at how that is done. How the IP addresses are allocated. So here actually like there can be like two different IP address structures. One is the private IP address. They range from 10 to 8, essentially like 10 or 8, and then like 10.000, 10.0.0.0 to 10.255.255.255, which is the maximum 8-bit number. Also like the other one is this 192 and 168, 192.168 or 16. That's another set of private IP addresses, and then 172.16 and that is another one too. So here it's listed here basically like 192.168.0.0 through all the way, and then this 172.16 that's again goes to 172.31.255. So this these IP address ranges essentially like so you can look at your machines inside the network, they will all have like these IP addresses being like 192 or 172. But the public address space is mostly like, I mean, it's there are many authorities assigning these numbers. Some of these authorities are this RIPE, ARIN, AFRINIC, etc. Or there are local internet registries, essentially they are also known as LIRs. In United States, there are several companies which allocate these addresses. Right now, like, I mean, even like new companies have started allocating these addresses. Essentially, like your provider actually like has taken a block of address from one of these authorities, and then they start allocating it to their customers as well. So essentially, like, I mean, the bottom line is you have a small block from whatever range that you have, and you subnet your networks. So essentially, you can think of the larger internet as a hierarchical element, where you may just get like one address space, and then basically like that from one address you create a subnet which has more of them. So, and then you create the subnet of subnet, and then you take that wider. So once you have this thing, like, I mean, you don't have to broadcast the address in a wide range essentially. So so now let's look at how do we address in the internet networks. So the problem that we face is essentially like, I mean, now we have more than one physical network because there are all the subnets and they are in different locations, large number of computers. So we need a structure in the IP addresses. So to define the structure, we need to have one portion which defines the network or the network part. This defines which identifies which network in the internet network that this belongs to, which is basically the internet. And then the second part of the address is the host that identifies the host on that network. So every network has an address. That's what the first part is, and then the second part is, okay, in this network, where does this host fit in? So now we talked about the 32-bit. Now this how do we divide this into hierarchical IP address, hierarchical division? So the network part defines the physical network that it belongs to, and then the host is identifies which is the host that is connected to that one. So here, like, I mean, we saw that in the previous slide there are these 4 numbers. The octets, basically the first 3 octets now determine the network, and then the last one determines what the host is. So essentially, like, I mean, even though, like, I mean, we talk about this, the boundary can be really anywhere. It may not be like even a multiple of 8 bits, because if you run out of the address space or the original ones, we can actually like allocate more to the host if there are more hosts on the network. And that how we determine what is the network part and what is the host part is by using a network mask. So let's look at what the network mask is. The network mask helps define which bits are used to describe the network part and which are used for the hosts. So there are different representations again for the network mask. You can define the network mask as just a decimal dot notation which is 255.255.224.0. This is one of the examples. So here you can see that actually like the network is up to here. That is the first 8, 16, the 21, sorry 19 bits, and then the remaining all the zeros are the host part. So the 19 bits, first 19 bits represent the network, and then the remaining ones in this like 13 bits represent the host address. Binary form, that's what shown here, and then the hexadecimal is also if you can describe the mask, which is FFFF E000. So typically, like I mean, your network will, once it assigns once you become a part of the network, when the host whatever your machine parts becomes a part of the network will assign a mask essentially based on how many computers in the network are in the network. Based on that it assigns a mask, and then the way that we generate the IP addresses is just a simple binary AND of the 32-bit IP address with the 32-bit net mask, and then we get the network part of the address. So here a simple binary AND will provide the first 19 bits, which is essentially the network, and then the remaining ones will be the host. So you can use just a simple AND function to actually separate out the network and the network address or network identification and the host identification. Let's look at the classless addressing. IP address with the subnet mask defines the range of addresses in the block. Essentially, so once you have these subnet masks, essentially like I mean the 10.1.1.32 or 28, that defines the range from 10.1.1.32 32 to 10.1.1.47 with the above subnet mask. So here the 10.1.1.32 is the network address, and then the 47 becomes the broadcast address, and then the 33 to 46, the range in between, they can be assigned to other hosts or as a address space. Actually they can be assigned as a network addressing network addresses that you can assign to. So now let's look at how the computers forward the packets based on these addresses. So when the packets are received, the computers can only send packets directly to other computers only if they are on the subnet. If the destination is not part of the subnet, which is identified by the network address, then they are sent to a gateway. The gateway is kind of, you can think of as a central router, and that actually sends it to the other networks. So gateway is something that communicates between the two networks, and then within the network the packets can be sent directly. And then the default router option in /etc/rc.config conf sets the default gateway for the system. So this is one thing that you can find out. You can do a less on this file to see where is your default gateway and what is the machine that is default gateway. And then basically, like I mean, IP forwarding on a free BSD box this is turned on with the gateway enable option in the etc rt.conf. Otherwise, the box will not forward the packets from one interface to another. So let's look at the DNS itself. So DNS is what is the domain name system. There the computers use the IP addresses, but again, like I mean, for humans, it's very hard to remember those IP addresses. So DNS provides a reverse mapping of the IP addresses to the machine names, and vice versa. I mean, actually, like it goes both ways. So this is something that basically that we can look into, and then we can see like what is the domain name of a particular IP, or if you have a domain name, then you can also convert it to what is the IP address of that. So this is the one. This is one of the lists where when the computers are moved between the networks, the IP addresses will change, but their domain names, the names remain the same. So like I mean, we saw like the Catper or whatever the name of the machine itself, that always remains the same in whichever network that goes into. So the way that we keep it that way is to use a domain name system file. So the DNS file, if you look at it, that will have the name listed, and we can easily see like I mean what is the map of this particular computer, this particular machine. So let's look at some of the useful commands that we can use to navigate the network. Here I am actually talking about few of the commands. Again, the commands actually follow the same same syntax that we all have all are familiar with by now, which is the command name followed by arguments followed by command name followed by options followed by the arguments. So the first command is ping command. Ping is used to send this ICMP echo request to network hosts. So essentially, it is actually a command by itself. Basically, it instructs the receiving computer to send an echo of the ping basically. So for example, if you want to see like I mean the network, if a particular machine is alive or dead, you can use a ping, and then you use the ping command to or you send the ping command to that machine, so that if the machine receives that ping command, then it sends you back a message saying that hey, I received it. So then you know that actually that machine is alive. If it is not, this it can go on pinging for a while, and then you know that either the network is having an undue delay, or if that machine is the machine that you are trying to reach is dead. So typically we do this before we send an FTP request. We studied the FTP like in the last lecture, which is the file transfer protocol for transferring files between systems, so doing that, actually we will be studying in more detail in the next section as to how FTP can be done and what are the different configurations for FTP. But the bottom line is, in order to the ping is used as a prelude to doing an FTP, just so that you can see whether the machine is alive, and then you can send a request. Netstat is another command. This prints out the network connections, the routing tables, the interface stats, etc. We know that all these things, all these terminologies we studied in the previous lecture. The routing tables are the tables where the machine knows okay how the IP addresses are mapping and what are the closest distances, and So how to quickly reach the destination. Essentially, like I mean, if it receives the packet from this particular computer or this particular IP address, what should be the next IP address? Those kind of that kind of information is in the routing table. The network connections, again, it prints out the nearest neighbors who are all connected and how they are connected, and also like the interface stats, like what kind of ports are open, which ports can be used for communication, things like that. If config is a command that is used for configuration of networks. So in if config, actually you can configure the network interfaces. There are good examples. If you do a man or if config, you should be able to get a lot of good information about this. Trace route is as a command to print the route that packets are taking to the network host. So as you know, like the internet itself is it's a big aggregation of the network hardware connected together by various gateways. We saw the gateway example and the machines. So the tracking the route that some packet is taking, some packet is following, it may be like very difficult. So here essentially, like I mean, this uses the IP protocol time to live field, one of the fields that we talked about when we talked about the IP address itself, and then it from there it attempts to see like the response from each of the gateway along the path, so that it understands what the path it takes to reach the destination. So here essentially the mandatory parameter is the destination host name or the IP address, the IP number. All the other ones basically you don't have to specify it, can assume some default and give you the result. Here usually it also sends out a probe datagram. We know like what the datagram is, essentially like where we specified in the IP layer and below. That datagram is typically it's a 40 byte data, and basically but given like I mean if it is more than sometimes it can be increased by specifying a packet length. So again, I will ask you to just do a man of trace route to get like more information regarding this particular command. Usually it gives you like I mean a bunch of hosts. It gives you the various it gives you as a DNS table essentially. Like, so it gives you the host name and its IP address, and then it also gives you like I mean how much time it is it's taking, like I mean how many hops each one is taking, and then what is the time that it is taking in each of the the host itself. So some of the LSF based commands use these commands as to call out certain things and to understand certain functions essentially. And the last command that we'll talk about is the TCP dump. TCP dumps the traffic on a network. Again, this um, the TCP dump actually prints out the headers of the packets on the network interface that match the Boolean expression. So you can also like give this Boolean expression. Again, this goes through like that same the options followed by the um, the argument. Here essentially like specify the options and then it dumps out that. So the TCP dump may not be a command that you can actually run it unless you have a super user permission or a system administrator permission. But you can still type man TCP dump and see like what it generates. It should generate a whole bunch of information essentially. So and there are various modes that by which you can dump information. So if you want to print all the packets arriving at a destination, you can give the TCP dump on that particular host, and then you can also say like okay, you want some preferential packets only like show certain things basically. Or you can also say like okay, this I want to see whether what is the traffic between two hosts. So again these are the commands that are mainly used by the system administrators to troubleshoot a lot of these issues. I just wanted to give you a flavor of how they do it and then what kind of thing goes on underneath. I hope this is useful for you. Again I think this is pretty much the end of today's lecture. We will be picking up from this point in the next one. Again, to summarize, today we mainly talked about the IP addressing. We talked about how the IP addresses are formed, why the IP addresses are needed, the 32-bit IP address. There is also the address of the IP or the address of your computer, which essentially constitutes two pieces of information. One piece of information is the subnet where it belongs to, the address of the subnet, and then the second piece is its own host ID inside that subnet. And even though this is represented as 4 8-bit numbers or 4 octet numbers, in reality the network address could be some bits of information and then the host ID can be a different set of bits. They all need to add together to the 32-bit, but inside the 32-bit however you can partition is up to you. And so typically like that is determined by this the subnet mask that we talk about, or the network mask. Essentially like by just looking at the network mask you can figure out how many bits are the addresses, how many bits are the part of the network address, and how many bits are part of your host address. So this I hope this is useful, and then we also saw some commands towards the end as how the system administrators use these tools effectively to manage the system. Again I just wanted to just remember, if you remember one command, that is the ping command, which you will be using many more times. All the other commands are very sparingly used by us in our field. Again, thanks a lot. Thanks for listening. We'll pick it up from this point in the next lecture. Thanks once again.